Thanks for the privilege and welcome again to another clips as we continue with studying subtopics in elementary set theory. In today's lecture, we are going to look at infinite sets and their cardinalities. Infinite sets and their cardinalities. Now, in our previous video, we have talked about finite sets and their cardinality, where we have said for a set to be finite, it means the elements thereof are countable. Now, and in our introductions, we have also given some examples where we have unknowingly made mention of some of these infinite sets. An example of such will be given. But first of all, what do we understand by an infinite set? Now, as the word implies, infinite means infinity. A set that tends to infinity. Uncountable. Something that tends to infinity is something we cannot count. Uncountable set. So a set where its elements cannot be counted or listed explicitly is called an infinite set or an uncountable set. Now, example of such is, let's consider, let's say Q, let Q be a set of all even positive numbers. Let Q be a set of all positive, even positive numbers. Then that set will be even positive numbers. So you say 2, 4, 6, 8, on we go, because we say all, and you can see that they tend to infinity. They are as many as such that we can't count. They are uncountable. Now, another example, let's say the set of all integers. The set of all integers. Set of all integers. So we say dot, 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 because to the left it also tends to infinity. So we have, say, this, also to the right it tends to infinity. Now let's also consider another set, say the set of whole numbers. And let's use W to denote that. Set of whole numbers. These include 1, 2, 3, 4, on we go, because it also tends to infinity. Now we can also consider another example is the set of natural numbers. Set of natural numbers. Let's use N to denote that. And that set consists of 1, 2, 3, 4, on we go. So you can see that these ones that we have listed differs from those that we consider in the case of a finite set. Now, in these ones, you can see that because they are uncountable, they cannot be listed, all the elements cannot be listed explicitly. So we have used 3 dots here, dot, 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 to indicate that, and so on. It doesn't end, and it tends to infinity. And in this case, you can see to the left, it tends to negative infinity, to the right it tends to positive infinity, and the same thing in the other cases. So what we have presented here is good, these are good examples of an infinite set. These are good examples of infinite sets. Now the next thing I want us to consider is, but first of all, before I continue, When trying to list them, as we did in the case of the finite set, you can see that for it to be a set, we said they must be enclosed in a curly bracket. And the one that they are in attempting to list each element, we can see that we have also separated them with commas. So this also conforms to what it takes to be a set. But tending to infinity, uncountable, makes it infinite. Now the next that we want to talk about is their cardinalities. The cardinality of an infinite set. Now, in our previous videos, we have also explained what cardinality means. We said cardinality simply means the size, the magnitude of a particular set. The magnitude, the size of a particular set. And we said we use these bars to denote it. So if we say we want to determine the cardinality, being that these are infinite sets and we are interested in the cardinalities of this set, it means the size, the number of elements in that set. Now in this case, we can't count them, they are uncountable, they tend to infinity. So the cardinality of Q, therefore, will be infinity. Now, in the case of a finite set, we observe that for the finite set, the cardinalities are also finite. It's a unique number. While for that of an infinite set, because they are uncountable, it's not a finite number, it's not a unique number, but rather is infinity. It's also applicable to this. The cardinalities of all these ones, just say W, set of whole numbers, is also infinity, and the cardinality of set of natural numbers is also infinity. These are all, their cardinalities are not finite. They are not finite, but rather they tend to infinity. Now, in our previous video, if we can remember, we also tried to compare the cardinalities of two sets. We tried to compare the cardinalities of two sets. Now, in this video, I want to tell us that it is not as easy as we did in the case of the finite set. In this case, it's a bit rigorous, it's a bit difficult to determine the cardinality of two sets. So what are we going to do? We are going to employ a logical reasoning by using, let's write it. Let's write something. When it comes to comparing two infinite sets, to know if they have the same cardinalities, if they have the same cardinalities, first, it is also difficult to do this. It's difficult to do this. Therefore, we can employ a logical reasoning. You can employ a logical reasoning by using the idea of bisection. by using the idea of bisection. By using the idea of bisection. Now, if we can remember, in our previous clips we have said, for the case of a finite set, we have said, two finite sets are said to have the same cardinality if and only if there exists a bisection. If and only if there exists a bisection. So with this, I am saying that it's not as easy as we did in the case of the finite. So in this case, we are just going to use the idea. But in doing this, we will assume that these presentations, as we have gotten, we will look at infinite sets in terms of countably infinite and uncountably infinite sets. We are going to determine infinite sets as countably infinite and uncountably infinite. Now, these ones that we try to list, though we are able to list all of them, all these ones that we attempt to write, they fall into the category of countably infinite. They are infinite though, but we can attempt to list them. These ones, we call them countably infinite sets. So first of all, let's compare if two countably infinite sets have the same cardinality. Now, in doing that, we have said that we are going to use the idea of bisection. If that is true, then we can in advance say that two finite sets or countably finite sets, two finite sets of countably finite sets are said to have the same cardinality if and only if there exists a bisection. Being that we said we are going to use the idea of bisection. So let's try to do something. Let's try to show if that is possible. Let's try to show if that is possible. Now let's consider a function. Let's consider a function f of n, say equals 2n, where n is an element is contained in the set of natural numbers, where n takes values from here. Now, if that's the case, as we did in the previous case for that of finite set, we know that these are the domain variables, and the output from here will be the range variables. So, meaning we have for n equals natural numbers, so 1, when n equals 1, you see that this one becomes 2. F of n becomes 2. Now, when these are the domain variables, let me just write them out. 1, 2, 3, 4, on. So we are saying that when n takes 1, you see that f of n takes 2. 2 times 1. Now when n takes 2, 2 times 2 becomes 4. When n takes 3, this times this becomes 6. And in like manner, this one becomes 8, and so on. Here we know that these are the domain variables, and here the range variables. Now in this case, you can see that In this mapping, there is one-to-one mapping. There is one-to-one correspondent. So this is a function and is injective. And you can see that all the elements in the range are also mapped. Therefore, we are saying that this one is also surjective. And in our previous video, we have concluded that if a function is injective and at the same time surjective, we are saying that that function is a bijective function, confirming the earlier statement that we have made. Though, if you look at it properly, you can see that the range values are a proper subset of the range values which we have as Q, the set of positive even numbers, Q, and this one, the set of natural numbers, N. You can see that these ones are contained in this. So this is a proper subset of this. But then they have the same cardinality. So this we can conclude by saying that the uncountably infinite sets have these uncountably infinite sets have the same cardinalities, because you can see that they are injective, the same time surjective. Therefore, we conclude that there exists a bijection. Now let's consider another function to see if we can also conclude that these cardinalities, they have the same cardinalities. Let's consider another function. Let's consider another function. Say f of n equals n plus 1, where n is an element is contained in the set of whole numbers. N takes values from here. Now, if that is true, as we have earlier stated, these are the domain variables, and what the output that we are going to have here will be the range variable. So let's write down the domain variables. We said it takes numbers from the whole numbers. So it says 0, 1, 2, 3, on. And these are the domain variables. Now, if this function takes this first element value, you see that the output will be 1. If it takes this one, the output will be 2. If it takes this one, the output will be 3. This one, the output will be 4. On we go. While this, if you look at it critically, you can see that the output values are set of natural numbers. But as we have earlier described, we can see that, as we have earlier described, you can see that the set of natural numbers are a proper subset, are also a proper subset of the set of whole numbers. So in this case, and in the mapping, we can also see that this is a function because all the elements in the domain variables are mapped out. And again, there is one-to-one correspondence, the mapping, which makes it injective, and all the domain range values are also mapped, which makes it surjective. And we have said if a function is injective and at the same time surjective, then we say that function is bijective. So there exists a bisection. So even in this one, we can conclude that for these two countably infinite sets, there exists a bisection because they have the same cardinalities. Now, lastly, let's also look at another function. Say this, where we have this. If we assume that n takes values, n is contained in the set of all integers. You can see that when you want to produce this, you can see that when you impute any value you impute, this absoluteness will make it positive. So you can see that the set of numbers that we are going to have in this case, the set of range values that we are going to have in this case will be set of natural numbers. Because when if you input -1 here, it will turn it +1. If you put +1, it's still +1. And in set theory, we are not allowed to repeat elements. So +1. So irrespective of the number you have here, you will have it in terms of positive. So the range values that we are likely to generate here are natural numbers. They are all natural numbers. I mean, they are all whole numbers. They are all whole numbers. Or you say natural numbers. Now, if that is true, we can conclude with a statement. Let's take a little note. We can conclude with a statement. Already we can see that from the examples that we have given, the countably infinite sets, they have the same cardinality because there exists a bisection. So with that I have given, we can conclude by saying that we can comfort with a generalized idea that for any two countably infinite sets, say n, set of natural numbers and set of integers, where the cardinality of the letter, which is this one, is where the cardinality of the letter is bigger than the former, and the former is n. And if the set n has the same cardinality, but a proper subset of the set of all integers, then we say that both countably infinite sets have the same cardinality, because we have shown that there exists a bijection. Whereas any set that has Whereas has a more greater cardinality than that of the countably infinite set is called uncountably infinite set. Now look at the closing remarks. I have said, with what I have shown, I have concluded, and concluding by saying that we can see that after imputing the domain values, you can see that one part is a subset, it's a proper subset. Like in this case, we can see that the output values, the range values, are a proper subset of that of the range values. It's a proper subset of that of the range values. Therefore, but then they still have the same cardinalities, irrespective of the fact that it's a proper subset. And in it, we saw that there exists a bisection. So if that concludes, we are saying that they have the same cardinalities. Whereas, if what we are looking at is not true, and you see that it's bigger, a particular side is bigger than what we have shown, and it's not really having the same cardinality, then we conclude that such a set is not a bijective function, but rather is called, it's not a countably infinite set, but rather it's called an uncountably finite set. That's the way we said. Whereas for any set that has more greater cardinality, as we have done in the case of the finite, countably finite set, we are saying that such a set is called an uncountably infinite set. Thank you very much for this class, as we look forward to having other subtopics. Thank you.